Next up, let's take a look at the selection sort. So selection sort, like the bubble sort we've already learned, is an algorithm for taking in a list of unsorted data and returning it in sorted order. Selection sort and the bubble sort in this way are both just a different way of accomplishing the same goal. The way selection sort does its work uses an algorithm that we learned in the previous video for finding the smallest item in a list. So recall we did a linear search through the list to find which item had the smallest value, and then we could return the index of that smallest value. The selection sort uses this algorithm to do sorting. The basic steps are, we start with an unsorted input list and some empty output list. Then we scan through the input list to find the smallest item. Once we've found it, we remove it from the input list and attach it to our output list. And then we go back and find the next smallest item. Move that, and then the next, and then the next, repeating until we've found all of the items from our input list and put them in the output list. Since we're finding the smallest, and then the next smallest, and then the next smallest, the order we're adding these into the output list will be in sorted order. For example, given some input list 741652, our selection sort algorithm starts by scanning this input list to find the smallest. So we look at the first item, that's our smallest so far. Then we look at the next item, that becomes our smallest so far. The next item's even smaller, so that's our smallest so far. We look at the next item, that's not smaller, not smaller, not smaller. So after scanning through the entire list once, note doing a linear search through our input list, what we're left with is the index of the smallest item in that list. Then we can just take that item and put it in our output list. And then start our process over on a now smaller input list. We say find the next smallest item. So starting at the beginning, looking through our list, we find the smallest item at the end of the list there, and then we copy that into our output as well. Repeating until we've found all of the items and put them in order. So note, for each individual item we're sorting, we had to do a linear search through the input list. So we had to check all of the items to find which one was the smallest. And then we had to check all of the remaining items to find the next smallest one, and so on. Notice if we want to find, for example, the third smallest item, it's not some special algorithm, it's still just finding the smallest item, but it's finding the smallest item after having removed the previous two smaller items. So the next smallest is now the overall smallest in what remains. So let's see how we can implement this in Python. So in the provided selection sort.py file, there's a bunch of base code here already. So I have a main function that's going to generate a random list of 15 values. So that calls this function that says generate a list of all of the values from 0 to 15, but then shuffle the order. So random.shuffle takes in a given list and rearranges it in place. So all the same items, just in different locations in the same list object. So that returns our random list, and we're going to use that to sort things. So we'll print out the unsorted list, then we'll call selection sort on that unsorted list, which should give us back a sorted list, and then we'll print out that sorted list. So the only things we need to implement here are the selection sort and find smallest functions. So note the find smallest is its own little subfunction that's part of the selection sort. So in terms of the design of the selection sort, as was described previously, what we're going to do is start with an empty list, and until our input is empty, we're going to remove items from our input and put them into our output, such that we're removing the smallest item each time and adding it to the end of our output. So we start off with an empty list, so we'll say create an empty output list, and then until the input list is empty, we're going to find the smallest item in the input, remove it from the input, and then append it to the output. Pretty straightforward. And then once we've done that for all the items, we can just return the output. So find the smallest, put it to the output, do it again. Notice finding the smallest, though, is a call to this other function, so we'll have to create that as well, but we've already seen how to do that. So we've seen how this works before, but let's just walk through it again. In terms of design, we need to start with some item as our smallest so far, and then we'll scan through the list, seeing if any of the other ones are smaller than that. So it doesn't matter which item we start with, but it makes sense to start with the first item. So we'll say start with the first item as smallest so far. And then for all other items, if smaller, then I'll just say keep that as the smallest so far. And once we're done, return the index of the smallest item. Okay, so to implement this, we start by keeping track of where the smallest item is in our list. So we'll say smallest index. This is the index of the smallest so far. And if we haven't looked at anything, we'll just say the very first item is so far the smallest item. Then we'll scan through all the other items. So I'll say for I in range from 1 to the end of our list, so len of list. And we say if the item that we're looking at is smaller than our smallest so far, so if list at I is less than list at smallest index. Notice we have to use these indexes to get the actual values. We don't want to just compare the indexes, but the values themselves. So if the current item is smaller than the smallest item we found before this, then this is the new smallest. So smallest index equals I. Once we've done that for all of the items in our list, so once we've traversed the whole list doing this check, then we know the smallest index variable will point to the location of the item that has the smallest value in our list. This is what's known as a loop invariant, that at the end of this loop we know this truth. Sort of like an assert, but it's an assert that we always know to be true because of the theory of what we've done here. So in this case, we know what the smallest index is. We can just say return smallest index. So if we have this find smallest function, now let's use it to do our sorting. So again, we have our design for this. We're going to start with an empty list and find the smallest over and over and over again, adding that to our empty list until it's no longer empty. So we'll say create an empty list here. That's output list equals an empty list, and until the list is empty. So we'll say while the length of our list, our input list that is greater than 0. As long as there's still items in our list, we're going to loop through and continue to check each one. Okay. Next, we want to find the smallest item in the input list. So we have a function for doing that. So we'll say find smallest on our input list. And that's going to return to us the index of that smallest item. So I'll call this smallest index again. Why not? So smallest index equals find the smallest. So we pass in our list. It tells us where the smallest item is. So now we want to use that to modify our input list and build our output list. So the smallest item, I'll say smallest value equals list.pop at the smallest index. So we found the smallest location, we're removing that, and that gives us the smallest item itself. And then we just append that. So we say output list.append smallest value. So if it's an empty list, doesn't matter where we put the smallest value. Now if we've done that once and we're now adding the second item into our list, that second item is going to be the second smallest, so it should come after the first item we added, so we're going to append to the end of our list. Now, once we've done that for all of the items, that is to say, once we've finished this loop and our input list is now empty, we can then return the output. So we'll say return output list. Now, the only real issue with this, assuming it works, is that we're destroying our input list. So each time we say list.pop, we're mutating the value that was passed into us, this list variable. And it's usually not the case that you want your functions to destroy their inputs, because we don't necessarily know how those inputs were being used outside of this function. So it's a good idea to not do that, and we've seen a way around that is just to make a copy. So we'll say list equals a slice from the beginning to end. So say shallow copy input to prevent destruction. We don't want to destroy that list. We want it to exist still in the calling program because maybe that's an important list for something else as well. So we'll say shallow copy to input to prevent destruction. All right, so let's save our code and try it out. Come down here and say Python selection sort.py. So given some input, which is clearly not sorted, we run through the selection sort and we get an output that is sorted. So it does the same thing as a bubble sort, but it does it in a different way. Notice also with the bubble sort, we were sorting the original list. So our unsorted list here would be the thing that was changed. In this case, we're returning a new list. So it's called sorted list, and that's the thing that is sorted, whereas our unsorted list remains unsorted. So whereas our bubble sort was an in-place sorting algorithm, our selection sort is not. Now we can modify the selection sort to become an in-place sorting algorithm, but I think I'll leave this as a homework exercise. The basic idea behind it, though, is instead of creating an empty list and moving items to that empty list when we find the smallest, we'll still find the smallest, but then we'll swap it to the front. Then we just keep track of the point in our list that separates the sorted section from the unsorted section. So we find the smallest item in the unsorted section and move it to the end of the sorted section. So we swap it to the front of the unsorted section, if you will. That way the original list still contains all the values, and the location of those values in the list is what's being sorted. But again, I'll leave that as a homework challenge. So in terms of efficiency, the selection sort algorithm is roughly equivalent to the bubble sort algorithm. And this is because in order to sort things, we have to do effectively a linear search for each item. So we have to run find the smallest, which is a function that traverses our input list, and it has to look at all of its items to determine which one is the smallest of those items. And if we have to do that find the smallest, which gives us one small item, which we then move into our output, and then we do the find the smallest again, if we have to call find the smallest for every item in our input, so if we have 100 items, we're going to say find the smallest 100 times. And if find the smallest is order n itself, we have to run that n times, then it's order n times n, or n squared time. So the selection sort, in the worst case, is very much like bubble sort. They both take quadratic time, or n squared time. The advantage of the selection sort, though, is we're going to do fewer swaps than bubble sort. Right? With a bubble sort, anytime we see two items that are out of order, we swap them, and then we do another pass, and they might swap again, and we do another pass, and they're going to swap again. So for any given item to move from, let's say, the beginning of the list to the end of the list is going to take n swaps to get it there. Whereas with selection sort, we're going to scan through the list, so we're still doing n comparisons, but the swapping operation, if this were a very expensive operation, we're doing far fewer of them. So we're going to scan through all the items, but then we're just going to take the location of the one item that we found and do a single swap to put it in its final location. So for each pass, we're doing n comparisons, but a single swap, for a grand total of n swaps, but still n squared comparisons. Whereas with a bubble sort, in the worst case, could be up to n squared swaps as well as n squared comparisons. So if swapping is a very expensive operation, then selection sort might be the best choice for you. For example, it's faster to read from flash memory, like a USB stick, than it is to write to that memory. So fewer write operations can save a bit of actual clock time, despite the algorithm complexity still being order n squared. Now again, this algorithm isn't doing exactly n squared comparisons, because the first time through we're comparing n items to determine which one is the smallest. But we've moved one of them to our output, so in the next pass, we're only checking through n-1 items, and then n-2, etc., etc. But if you sum all of those up, that ends up being n squared plus n divided by 2, which is still on the order of magnitude of n squared. So if the problem size goes up by 10 times, the algorithm is still going to take roughly 100 times longer to execute. That is to say, bubble sort and selection sort will take roughly the same amount of time in the worst case.